On the morning of June 8, 2026, the seafloor off the southern coast of Mindanao moved, and the southern Philippines felt the strongest earthquake to strike the country in nearly 50 years. The magnitude reached 7.8. The shaking near the coast lasted only about a minute. What came after is the reason for this report. In the days that followed, that same stretch of seabed gave off more than 8,000 aftershocks. Several were strong enough to count as major earthquakes in their own right. To the people feeling them arrive, one after another, it seemed like the ground had stopped obeying any rule at all. If these calm reports are worth your evening, you are welcome to subscribe and follow along. The ground was obeying its rules the whole time. That is the quiet centre of this story. Over the next 2 hours, we will go through what happened off Sarangani, why this one patch of the planet shakes the way it does, and what the science says is still to come. At 37 minutes past 7 in the morning, the seafloor about 20 miles south of Sarangani gave way. The break sat offshore, under the water at the southern tip of Mindanao. It was a Monday, and most of the region was already awake. Children were in classrooms, markets in General Santos were open, fishermen were back at the shore or still out on the water. Then the ground began to move, and it kept moving for close to a minute. A minute is a long time in an earthquake. Most strong quakes shake hard for 10 or 15 seconds. This one ran far longer, because the fault below did not snap all at once. It tore along its length, section after section, for about 70 seconds before it stopped. People in General Santos said it was the strongest shaking they had ever stood through. Furniture walked across floors, shelves emptied, cracks opened in the walls of newer buildings that had never been tested like this. The Philippine Institute of Volcanology and Seismology first put the size near magnitude 7. Within the hour they raised it. The United States Geological Survey and the European agency that tracks these events both settled on magnitude 7.8. That number matters, and it is worth slowing down on, because each step up the magnitude scale is much bigger than it looks. A 7.8 is not a little stronger than a 7. It releases close to 15 times more energy. This was a great earthquake, the kind that reshapes coastlines and gets studied for years. It was also the strongest earthquake to strike the Philippines in nearly 50 years. You have to go back to the 1970s, to a quake in the Moro Gulf that killed thousands, to find a larger one in this country. For almost everyone living in the South today, this was the biggest they had ever felt, and the biggest their parents had felt. A whole region met something it had no memory of. The early reports came in the way they always do, scattered and unsure. Local disaster offices counted what they could see. Roads cracked in South Cotabato. A national highway in Tantangan split along its surface. In General Santos, about 15 miles from the break, the shaking reached the level the official scale calls destructive. Power flickered. Phone lines jammed as everyone tried to reach everyone at once. Out at sea, something else had started. When the fault moved, it lifted and dropped the water above it, and that motion began to travel toward the shore as a wave. The Institute did not wait to measure it. Minutes after the quake, it raised a tsunami warning for the coasts of 9 provinces in the south, and told people near the water to climb to higher ground. We will follow that wave in its own chapter, because it has a clear story, and because it ended better than it might have. Here is the part that turned a single bad morning into something stranger. The big quake stopped, but the ground did not settle. It kept shaking. Not once or twice in the calming way a struck bell fades, but again and again, hour after hour, with shocks strong enough to throw people back to the floor each time they tried to stand. By late morning, the Institute had already logged more than 100 separate tremors from this one event. Some were small, a few were large enough that, on any ordinary week, each one alone would have led the news. That is where the title of this report comes from. To the family standing in the street, afraid to go back inside, it felt as if the earth had lost its sense of when to stop. A great quake is supposed to be one event. This felt like dozens, refusing to end. It only felt that way. None of it broke the rules that govern how the ground behaves. Every shock that followed has a name, a cause, and a pattern that scientists have watched in earthquake after earthquake for more than a century. The reason this particular sequence ran so hot and threw out so many large shocks so fast comes down to where it happened, in one of the most tangled corners of the planet's crust. To understand why the ground kept shaking, we We start with the first 2 hours, when the worst of the aftershocks arrived almost on top of one another. The main shock ended near 7:38 in the morning. The next strong jolt did not wait long. Within about 90 minutes, the same patch of seafloor produced 3 more earthquakes that would each be a headline on their own. One reached magnitude 6.5, 2 more reached magnitude 6. These are not gentle tremors. A magnitude 6 earthquake can crack buildings and bring down weak walls by itself. Here, 3 of them landed inside an hour and a half, stacked on top of a region that had just been hit by something far larger and was already full of damaged, leaning structures. Picture the timing from the ground. You have survived the worst shaking of your life. You're outside, checking on family, looking at the cracks in your home and wondering if it will stand. The dust has barely settled. Then the street moves again, hard, and you do not know if this is a new disaster or the old one returning. Then it happens a 3rd time, then a 4th. By 11 that morning, the Institute counted 138 separate shocks, ranging from the barely noticeable up to that magnitude 6.5. This is the heart of why people felt the Earth had stopped following any rule. A 2nd strong quake feels like bad luck. A 10th feels like the ground is broken in some deeper way. By the 20th, reason starts to slip, and fear takes its place. Officials saw this and spoke to it directly. They asked people to expect aftershocks, to treat each one as real, and to stay out of cracked and weakened buildings rather than rushing back in during a lull. That advice was not caution for its own sake. The danger from a sequence like this is rarely the first quake alone. It is the buildings that the first quake wounds and the aftershocks then finish. A wall that holds through the main shock with a hairline crack may come down on the 3rd or 4th strong shake. Many of the injuries and deaths in earthquakes of this size come from exactly that pattern, from people caught when a damaged structure finally gives way during an aftershock. So the steady stream of large shocks was not only frightening, it was hour by hour the most dangerous thing about the whole event. There is a measurement worth bringing in here, because it puts the early hours in scale. In the first day, the rate of shaking was extraordinary. The Institute was logging shocks faster than once every 10 minutes for long stretches. That is normal for the opening of a great earthquake sequence, and we will get to why it is normal. But normal on paper and normal underfoot are very different things. On paper, it is a falling curve. Underfoot, it is a region that cannot get a single calm hour to breathe. The fishing towns along the Sarangani coast felt it worst, because they sat closest to the break. Inland, in General Santos and across South Cotabato, the shocks arrived softer but still often. People in Davao Occidental, across the water to the east, felt the same restless ground. Tens of thousands of families made the same choice that first day. They left their houses and stayed out, in yards, on roadsides, in open fields, anywhere a falling roof could not reach them. What they were living through has a clean scientific name. The big quake was the main shock. Everything strong that came after it, including those magnitude 6 events, were aftershocks. That word sounds small, almost like an echo. It is not small, and it is not an echo, and the next chapter is about what it actually means. Because the moment you understand what an aftershock really is, the impossible feeling part of this story starts to make plain sense. An aftershock is an earthquake. That is the first thing to fix in place because the word hides it. When a large fault breaks, it does not relieve all the strain in the rock around it. It relieves some, and it shifts the rest. The ground near the break is left in a new and uneven state, with stress piled up in places that were balanced the day before. That leftover stress does not stay put. It finds the weak spots in the rock and lets go, one patch at a time. Each of those small releases is its own earthquake. Together, the swarm of them is what we call aftershocks. So an aftershock is not a leftover tremor from the first quake, the way a struck drum keeps humming. It is a fresh break in the ground, in a new spot, caused by the way the main break rearranged the forces around it. That is why an aftershock can be strong. It is real seismic energy, released by real rock moving, and there is no rule that says it must be gentle just because a bigger quake came first. This is the misread that fuels the fear. People hear aftershock and expect something fading and minor, a few rattles that taper off by lunch. When the shocks instead come hard and keep coming, it feels wrong, like the ground is doing something it is not allowed to do. But the ground is doing exactly what stressed rock does. The expectation was off, not the Earth. It helps to picture the fault as a long crack that just slipped. Along most of its length, the two sides moved and found a new resting place. But a fault is not smooth. It has rough patches, bends, and spots where the two sides locked instead of sliding. Around each of those, the strain is now higher than before. Over the following hours and days, those stuck patches break too in their own time, and each break is an aftershock. The bigger and rougher the main break, the more of these stuck patches it leaves behind, and the busier the sequence that follows. That is the first clue to why this event was so loud after the fact. A magnitude 7.8 is a very large break. It tore for about 70 seconds across a long stretch of the boundary between two slabs of the planet's crust. A rupture that big leaves a great deal of rearranged stress behind it, spread over a wide area. More disturbed rock means more aftershocks, plain and simple. The size of the sequence was set in part the moment the main shock ended. Here is a fact that surprises people, and it is worth saying plainly rather than saving. The line between a main shock and an aftershock is not fixed in advance. Seismologists only know which quake is the main shock after the fact, because the main shock is simply the largest one in the sequence. If a later shock had been bigger than the 7.8, scientists would have relabeled the whole thing. The first quake would have become a foreshock, and the new giant would have become the main shock. The names follow the sizes. The Earth does not plan them. That has a quiet consequence for the people living through a sequence. In the first hours, no one can promise that the largest shock has already come. The odds favour it strongly, once a great quake has struck. But the guarantee does not exist, and honest agencies do not pretend it does. This is one of the few places where the science stays openly uncertain, and we'll come back to that uncertainty near the end, because it shapes what people should do while the ground is still busy. For now, hold on to the simple version. Every shock after the big one was a true earthquake, born from the stress the big one left behind. None of them broke any law. The next question is the one the title really asks. If this is also normal, why were there so many, and why were some so strong? The answer starts with counting, and the count from off Sarangani is genuinely hard to picture. By the middle of June, the Institute had recorded more than 8,500 aftershocks from this one earthquake. Sit with that number for a moment, because it is easy to read past. 8,500 separate earthquakes in under 2 weeks from a single event. That is more than 500 a day on average. In the busiest early stretch, they came far faster than that. Most were too small to feel, the kind of shock that only a sensitive instrument notices. But the count itself tells you how much rock was disturbed and how widely the stress had spread. Of those thousands, 3 crossed magnitude 6. The largest sat near magnitude 6 and 7/10. That one shock, the strongest aftershock, would on a calm week be a serious earthquake in its own right, large enough to damage buildings and frighten a city. Here it was just the biggest member of a crowd. Below it sat a long ladder of shocks, dozens in the 5s, hundreds in the 4s, thousands smaller still, all the way down to tremors you could only know from a screen. There is a shape hidden in those numbers, and it is the same shape every large earthquake leaves behind. For every one big aftershock, there are about 10 that are a step smaller, and about 100 that are a step smaller than those, and about 1,000 smaller again. The shaking sorts itself into that steady 10-fold ladder, with many small steps for every large one. It holds across earthquakes all over the world, in different rock, on different faults. The Sarangani sequence followed it closely. That is part of how scientists could look at the chaos underfoot and still call it ordinary. The count climbed for another reason worth naming. The Institute runs a dense network of instruments, with 128 seismic stations spread across the country, and several close to Sarangani in General Santos, Kidapawan, Cotabato City and Davao. The more sensitive your instruments and the closer they sit, the more small shocks you catch. A weaker network would have logged a few thousand of the larger aftershocks and missed the rest. So part of that huge number is not the Earth being unusually wild, it is the watchers being unusually good at hearing it. The shocks were always there. Better ears simply counted more of them. Around the world, the very largest earthquakes can produce aftershock counts that run into the tens of thousands over months. A great quake in Japan or Chile leaves a sequence that ticks on for a year or more. Against that backdrop, 8,500 shocks in 2 weeks from a 7.8 is high, but it is not off the map. It sits in the range you would expect for a great earthquake on a busy plate boundary, in crust that was already stressed and cracked from a long history of shaking. The honest part is that the count is still rising. The sequence was not finished by mid-June, and it will not be finished for some time. Officials said the felt aftershocks could continue for weeks, and the smaller ones for longer than that. A sequence this large does not switch off. It winds down, slowly, along a path that is steep at first and then very gradual, like a long tail trailing off toward the horizon. That winding down has a precise shape, and it is the single most useful idea for anyone trying to understand what comes next off Sarangani. It tells you, roughly, how many shocks to expect tomorrow if you know how many came today. It is more than a century old, simple enough to hold in your head, and it turns the frightening question of when this will stop into something you can actually reason about. That pattern is the subject of the next chapter. Aftershocks fade in a way that was worked out before the year 1900. A Japanese scientist named Fusakichi Omori studied the shocks that followed large quakes and noticed something steady in them. The rate of aftershocks drops off quickly at first, then more and more slowly as time goes on. Roughly, if you have a certain number of shocks on the first day, you get about half as many on the second, a third as many by the third, and so on, the count thinning along a smooth curve. The pattern has held so well for so long that it carries his name. It is one of the few genuine laws in the study of earthquakes. What makes it useful is that it turns dread into arithmetic. Without it, an endless string of aftershocks feels like it could go on forever, with no way to know. With it, you can look at how the shaking has slowed so far and make a fair guess at how it will slow next. The first day off, Sarangani was violent, with shocks coming faster than one every 10 minutes at the peak. Omori's pattern says the second day should be calmer, the first week calmer still, and the second week quieter again. That is exactly what the Institute saw. The fall was steep early, then gentle, just as the curve predicts. The reason behind the curve goes back to the stressed rock from the earlier chapter. Right after the main shock, a great many patches of crust are sitting over their limit, ready to break. The most overloaded ones go first, fast, in the opening hours. That clears the easiest failures and leaves the patches that need a little more time. As the days pass, fewer and fewer spots remain close to breaking, so the shocks spread further apart. The ground is working through a backlog, and the backlog shrinks. There is a hard truth folded into this gentle curve. Because the tail is so long and so slow, the sequence never quite ends on a clean day. It thins until the aftershocks blur back into the region's normal everyday rumble of small quakes. Southern Mindanao is seismically busy at the best of times, so at some point, weeks or months from now, the last true aftershocks of this event will simply become indistinguishable from the background, and no one will be able to point to the exact day it finished. It does not stop so much as it dissolves. The long tail carries a real risk too, and officials were careful about it. Even far down the curve, when the shocks have grown rare, the occasional large one can still strike. A sequence can be quietly fading for 2 weeks, and then throw out a strong shock that undoes a damaged building someone had just begun to trust again. The fading of the average does not mean the danger of the individual shock is gone. That is why the guidance to avoid cracked structures held for so long after the main shock, well past the point where the ground felt calm most of the time. It helps to think of the curve like a hard rain that is easing. In the first hour after a downburst, the drops come so fast you cannot count them. An hour later, it is a steady fall. By evening it is a drizzle, and by the next day only the odd drop, though a heavy one can still catch you. The storm is clearly ending, yet you would not call it over and leave your shelter while drops still come. The ground off Sarangani is in the drizzle now, with the odd heavy drop still possible. Omori's pattern tells you how often the shocks come. It does not tell you how big any one of them will be. For that there is a second rule, just as old and just as steady, and it speaks directly to the part of this event that unsettled people most. It explains why a magnitude 7.8 could give birth to a magnitude 6 and 7/10, and why that too was something the science fully expected. The largest aftershock is almost always about 1 step smaller than the main shock. This is the second old rule, named for the seismologist Marcus Both, who noticed it holding across sequence after sequence. Take the size of the main shock, drop it by a little more than 1 full magnitude step, and you get a fair estimate of how big the strongest aftershock will be. The rule is not exact. It is an average drawn from many earthquakes, but it is steady enough to lean on, and off Sarangani it landed almost perfectly. Run the arithmetic on this event. The main shock was magnitude 7.8, one step and a bit below that puts the expected largest aftershock somewhere in the high sixes. The strongest aftershock recorded was near magnitude 6 7/10. That is squarely where the rule said it would be. So the shock that frightened people most, the one big enough to be a disaster on its own, was not a sign of something going wrong. It was the sequence behaving like a textbook. Why a full step down, and not closer to the main shock or much smaller? It comes back to how much energy the main break leaves behind in any single stuck patch. The main shock is the biggest possible failure the loaded fault could produce in one go. The aftershocks work on what is left over, on the smaller locked spots and the freshly stressed edges. None of those leftover patches is as large as the whole fault that just slipped. The biggest of them can still be substantial, about a step down, but not equal. There simply is not enough stored strain in any one remaining piece to match the main event. That one-step gap matters more than it sounds, because of how magnitude works. A drop of 1 magnitude is a drop of more than 30 times in energy, so even the strongest aftershock carries only a small fraction of the main shock's power. The 6 7/10 off Sarangani, frightening as it was, released far less energy than the 7.8. That is the quiet reassurance hidden in Both's rule. Once a great earthquake has struck, the worst is very likely already behind you, by a wide margin, even though strong shaking can still return. It is worth being honest about the word almost, because the rule is built on averages and the Earth does not read the textbook every time. Now and then, rarely, a quake that everyone took for the main shock is followed by something bigger. When that happens, the labels flip, as we saw earlier. The first quake becomes a foreshock and the new giant takes the title of main shock. After a magnitude 7.8 on a boundary like this, that outcome is unlikely. But unlikely is not impossible, and the Institute did not claim otherwise. It told people to prepare for aftershocks and to keep clear of weakened buildings, precisely because the small chance of a strong shock was still real. There was a historical echo on people's minds here, even if few said it aloud. This same region produced a far larger earthquake in the past, the Great Moro Gulf quake of the 1970s, which reached magnitude 8 and brought a deadly wave. The crust here can clearly make events larger than a 7.8, so the fear that a bigger one might still be coming was not foolish. It was just, by the rules of how sequences usually run, a long shot, and the science said so plainly while refusing to promise the impossible. Both's rule and Amori's pattern together answer most of the title's challenge. One explains why there were so many shocks and how they fade. The other explains why the strongest aftershock was as large as it was. Both say the sequence was ordinary in its behaviour. What was not ordinary was the place. To see why this corner of the planet was so primed to shake, we have to leave the aftershocks for a while and look at the break that started it all, and at the slow machinery underneath that built the strain over thousands of years. The main shock came from one slab of the Earth's crust grinding down beneath another. The fault that slipped was a thrust fault, the kind where one block of rock is pushed up and over another along a sloping surface. Under the sea south of Sarangani, 2 great pieces of the planet's outer shell meet, and one is sliding down under the other. For a long time the boundary between them was locked, held in place by friction, while the slow push of the plates kept loading it with strain. On that Monday morning the locked patch failed. The upper block lurched up and forward, the strain of years let go in seconds, and the shock raced out through the ground as the earthquake. The break was not a single point giving way. It was a tear that travelled. The rupture started at one spot on the fault and ripped along the boundary for about 70 seconds, unzipping a long stretch of locked rock as it went. That is why the shaking lasted so long near the coast. The fault was still breaking foot after foot, while the early waves were already shaking General Santos. The total energy released was enormous, far beyond what any human source could match, the product of a fault surface many miles across slipping all at once. The depth of the break matters, and here the agencies gave slightly different numbers, which is worth being straight about. The Philippine Institute placed the quake about 20 miles down. The United States Geological Survey placed it deeper, closer to 34 miles. Both are estimates, drawn from how the waves arrived at instruments near and far, and a gap like this between agencies is normal in the first days of a great quake. What both agree on is that this was not a shallow surface crack. It happened well down inside the descending slab and the rock above it, which is exactly where a subduction boundary does its largest work. Depth shaped how the quake was felt. A break 20 to 30 miles down spreads its energy over a wider area than a shallow one, so the shaking reaches farther, but hits any single near point a little less savagely than a shallow quake of the same size would. People felt this event across a huge swath of Mindanao, from the Zamboanga Peninsula in the west to the Davao region in the east, and faintly as far as Leyte to the north. A shallower 7.8 might have flattened the area right above it more completely while reaching less far. The depth here traded some local violence for a broader spread. There is a single measurement that captures the raw size of what happened, and it is worth translating into plain terms. Scientists describe the strength of a quake by its seismic moment, which combines how large the fault was, how far it slipped, and how stiff the rock is. For this event, that figure was vast, the signature of a great earthquake. The simplest way to hold it is the magnitude itself. 7.8 means this one shock released more energy than hundreds of the moderate quakes that rattle the region in an ordinary year, all spent in about 70 seconds. All of that explains the main shock as a thing in itself, a great thrust break on a locked boundary. But it does not yet explain why this boundary was here, why it was loaded, or why the sequence afterward ran so hot. For that we have to follow the slab downward and outward, to the trench that marks where one plate begins its long descent beneath Mindanao. That trench has a name and a character, and it is the next piece of the map. The trench off southern Mindanao is called the Cotabato Trench. A trench is the surface mark of subduction, the place where one slab of the planet's crust bends and dives beneath another. Out under the water southwest of Mindanao, an old piece of ocean floor is sinking down into the earth, sliding under the island along a sloping boundary that reaches deep into the hot rock below. The Cotabato Trench is the seam at the top of that dive, a long furrow in the seabed running off the coast. The main shock happened on the boundary where that diving slab meets the rock of Mindanao. Subduction is the engine behind the largest earthquakes on Earth. When one plate slides under another, the contact between them does not move smoothly. It sticks, locks, and loads, with strain over decades and centuries, then breaks all at once in a great lurch. Every one of the planet's truly giant earthquakes, the magnitude 8s and 9s, has come from a subduction boundary like this. The 7.8 off Sarangani was a smaller member of that same violent family, born of the same stick-and-slip machinery. The slab going down here is old and cold, a slice of ocean floor from the Celebes Sea to the southwest. As it bends into the trench and slides under Mindanao, it drags on the rock above and pushes the whole region into slow compression. That compression is what loaded the fault that broke. You can think of it as a vast, patient vice, squeezing the southern edge of Mindanao a little more each year, until a locked patch can hold no longer and gives way in seconds. The vice does not stop after a quake. It keeps squeezing, which is why the region will load again and break again in the centuries to come. The same subduction that breeds the earthquakes also built the land. As the slab sinks, it heats, and fluids cook out of it and rise into the rock above, melting it into magma. That magma feeds a line of volcanoes inland, the chain that includes Mount Apo, the highest peak in the country, along with Matutum and Parker near Sarangani. So the trench, the earthquakes, and the volcanoes are three faces of one process. The Institute was careful to note that this quake was tectonic, a matter of slipping rock and not of magma, and that it saw no sign the shock had stirred the nearby volcanoes. But the deep link between them is always there in the background of this landscape. Here is the detail that begins to set this place apart. The Cotabato Trench does not run alone or in a tidy line. It is one of several trenches crowded into the seas around southern Mindanao, each marking a different slab going down in a different direction. To the east, the Philippine Sea Plate dives the other way along the Philippine Trench. To the south, another boundary takes over. These are not far-flung features. They are packed close together, near the southern tip of the island, where several pieces of the planet's shell are all converging at once. That crowding is the key to the whole story. A simple coastline with one trench produces earthquakes that are bad enough. A spot where 2 or 3 trenches nearly meet produces something more tangled, with faults at odd angles and slabs stacked at different depths, all able to shed stress onto one another. The Sarangani quake happened very close to one such meeting point, where the Cotabato Trench runs up against the northern end of another older trench. To understand why the aftershock spread so widely and ran so hot, we have to look at that junction directly, and at the strange double-sided machine just to the south of it. The main shock struck close to where 2 trenches meet. The Cotabato Trench, coming up from the southwest, runs toward the northern end of a second great seam called the Sangihe Trench, which stretches south toward Indonesia. Near the southern tip of Mindanao, these 2 boundaries come close together, along with the start of a third. The seafloor here is not a single clean fault line. It is a knot, a place where slabs diving in different directions crowd into the same patch of the planet. The Sarangani earthquake happened inside that knot. Because of the knot, scientists were careful in how they described the break. The Institute and the United States Geological Survey agreed the quake came from thrust faulting on a steeply sloping fault, driven by subduction, but they left open exactly which boundary did the work. The rupture may have run on the southern part of the Cotabato Trench, or on the northern part of the Sangihe Trench, or most likely on some combination of the two where they join. In a tidy setting, you can name the single fault that broke. Here, the honest answer is that the break crossed a tangle, and the precise split between the 2 trenches is still being worked out. That uncertainty is not a failure of the science, it is a true reflection of the ground. When boundaries meet at an angle and slabs overlap, a single great rupture can step from one structure to another as it travels, breaking a piece of one trench and a piece of its neighbour in the same 70 seconds. The waves such a break sends out are more complex than those from a simple fault, and untangling them takes time and many instruments. The first reports give a fast, rough picture. The detailed map of which patch slipped, and by how much, comes later, from careful study. The junction also helps explain the breadth of the aftershocks. When a rupture spans a meeting of trenches, it leaves rearranged stress not on one clean fault but across a whole crowded zone. Stuck patches on the Cotabato side and on the Sangihe side both get loaded. Faults at odd angles woven through the knot each feel the change. So the aftershocks did not line up along a single tidy strip the way they do after a simple quake. They scattered across a wide patch of seafloor, lighting up many structures at once, because many structures had been disturbed at once. The spread that looked chaotic was the map of a tangle being shaken loose. There is a deeper reason this junction is so loaded, and it lies just to the south, in the sea between Mindanao and the islands of eastern Indonesia. That body of water sits over one of the most unusual pieces of tectonics anywhere on Earth. It is the place where the Sangihe Trench's slab comes from, and what is happening there is so strange that for a long time scientists found it hard to credit. It is the only spot on the planet where an entire plate is being swallowed from both sides at once. That double-sided machine is what built the strain in this whole region, and it is the closest thing this story has to a genuine oddity of nature. The aftershocks off Sarangani were ordinary in their behaviour. The ground they happened on is anything but. To see why this corner of the world is wound so tight, we go south, into the Molucca Sea, and look at a plate that is disappearing in 2 directions. In the Molucca Sea, a plate is sinking beneath the crust on both of its sides. Almost everywhere else on Earth, subduction is one-sided. A plate dives beneath its neighbour in a single direction, down one trench, and that is that. The Molucca Sea breaks the mould. Here the plate in the middle, the Molucca Sea plate, is bending down and sliding under the land on its west and under the land on its east at the same time. 2 trenches face each other across the sea, and the plate between them is being consumed from both edges, like a sheet of dough pressed and folded down on either side. Scientists call this divergent double subduction, and this is the only active example of it known anywhere on the planet. The result is as strange as the cause. The Molucca Sea plate has very nearly vanished. Over millions of years, both edges have fed downward into the hot rock below, until the slab now hangs beneath the sea in the rough shape of an upside-down arch, its 2 flanks plunging away in opposite directions. At the surface, the 2 volcanic arcs that rode above each diving edge have been carried toward each other as the plate between them shrank. They are now closing in, an arc on the west and an arc on the east, with the last of the sea floor being pinched out between them. The land is, slowly, collapsing inward on a sea that is being eaten from beneath. The western edge of this machine is the Sangihe Trench, the same trench whose northern tip reaches up toward Sarangani. So the boundary that may have helped break in this earthquake is the leading arm of the strangest subduction system on Earth. The slab going down the Sangihe side is ancient, one of the oldest still actively sinking anywhere, and it reaches enormously deep, hundreds of miles down into the mantle. A boundary with that much slab pulling on it from below is under relentless heavy strain. It does not need much encouragement to break. This is the real answer to why the region around Sarangani is so primed to shake. The southern tip of Mindanao sits where this double-sided machine to the south runs into the more ordinary subduction of the Cotabato Trench to the north. Several slabs, diving in several directions, all crowd into one corner. The crust there is squeezed, sheared, and bent from more than one side at once. Strain does not build along a single clean fault, but across a thicket of them. When something finally lets go, it lets go in a place already loaded by several engines working together. It would be easy to take this strangeness too far, so it is worth saying plainly what it does and does not mean. The unusual geology does not make the earthquakes break any special rules. A thrust fault here slips the same way a thrust fault slips anywhere, and the aftershocks fade by the same Amori curve as everywhere else. What the double subduction does is load the region harder and tangle it more thoroughly than a simple coastline ever could. It sets the stage. The actors still follow the ordinary script. That distinction is the whole point of this report, and it is worth holding as we go on. The behaviour was normal. The setting was extreme. A great quake on a tangled, double-loaded junction was always going to throw out a long, wide, vigorous swarm of aftershocks, exactly the kind that feels impossible from the street. The next chapter ties that knot together directly and shows how this crowded crust turns one great break into a storm of smaller ones spread across the sea. Stress from the main shock had many places to go, and that is why the aftershocks ran so hot. In a simple earthquake, on a single fault in calm crust, the rearranged stress from the break has a limited number of nearby places to land. The aftershocks cluster along the fault that slipped, fade by the usual curve, and the sequence stays fairly tidy. The Sarangani quake had none of that simplicity working for it. It happened in crust threaded with faults at many angles where slabs overlap and trenches meet, so the stress from the break had a crowded neighbourhood of weak spots to push on. A great deal of disturbed rock, plus a great many faults to receive the disturbance, adds up to a great many aftershocks. Think of the difference between dropping a stone into a still pond and dropping it into a pond already full of floating logs and reeds. In the still pond, the ripples spread out in clean, fading rings. In the crowded pond, the ripples hit every log and reed, and each one bobs and knocks against its neighbours, so the disturbance spreads in a tangle and takes far longer to settle. The crust off Sarangani is the crowded pond. The main shock was the stone, and the thicket of faults around the junction was the floating clutter that turned one clean splash into a long, messy churn. This crowding shaped where the aftershocks appeared. Rather than tracing a single neat line, they scattered across a broad patch of seafloor near the junction, lighting up structures on more than one trench. Some clustered south of Sarangani, near the heart of the break. Others spread along the boundary in both directions. Each cluster marked a different stuck patch or a different small fault that the main shock had pushed past its limit. The wide, untidy spread was not the ground misbehaving. It was the honest footprint of a quake that had disturbed a tangle rather than a line. The same crowding is why several aftershocks were so large. On a simple fault, the leftover stuck patches tend to be modest, so the aftershocks stay small to middling. In a junction loaded by several slabs, some of the stuck patches are themselves substantial faults, capable of producing a magnitude 6 on their own when the main shock pushes them over. That is how this sequence managed 3 shocks above magnitude 6 in its first stretch, including the 6 7/10. The setting did not just make many aftershocks, it made room for big ones. There is a measurement that hinted at how much the crust had been rearranged, and it showed up at the shoreline rather than on a seismograph. Along part of the Sarangani coast, the land rose. The seafloor near the break lifted during the quake, and the change was large enough to shift the tide line and leave parts of the shore standing higher and drier than before. That uplift is direct evidence of how much the ground moved and how the stress was redistributed. We will look at it closely in its own chapter, because for the fishing families along that coast it became a daily, visible reminder that the earth beneath them had been remade. Pulling the threads together, the picture is consistent. A very large break in crust crowded with faults, at a junction loaded by an unusual double-sided subduction machine, was always going to produce a long, wide, hard-running aftershock sequence. Every part of that sentence is ordinary physics. The only thing out of the ordinary is the place where all of it came together at once. The shocks that felt impossible were the predictable product of an extraordinary patch of ground behaving in entirely ordinary ways. There is one more thread from that first morning that we set aside and now need to follow, because it travelled far beyond the shaking. When the fault lifted the seafloor, it lifted the water too, and that water began to move toward the coast. The wave that followed is the next part of the story, and it is one of the few parts of this event that ended better than it could have. When the seafloor jumped, it shoved the water above it, and a tsunami began. A tsunami is not a wind-driven wave like the ones surfers ride. It is the whole column of water, from surface to seabed, set moving at once when the ocean floor suddenly rises or drops. The thrust brake off Sarangani lifted a large patch of seafloor in seconds, and the water sitting on top had nowhere to go but outward. That push spread away from the break in all directions as a long, low wave racing across the open sea far faster than any boat, then slowing and piling higher as it reached the shallows near the coast. The Institute did not wait to see the wave before acting. Minutes after the quake, it issued a tsunami warning for the coasts of 9 southern provinces, naming Sarangani, Davao Occidental, Sultan Kudarat, South Cotabato, and several others, and told people near the water to move to higher ground at once. Speed is everything with a local tsunami. The break was close to shore, so the first waves had only a short distance to travel, which meant people had very little time. The warning had to go out on the strength of the earthquake alone, before anyone could measure the sea, because waiting for proof would have wasted the few minutes that mattered. The waves came. Tide gauges and coastal observers recorded them along 6 areas of the southern Mindanao coast, with heights around 4.5 feet at the largest. Smaller waves reached farther afield, registering in parts of Indonesia, in Palau, and even faintly in Japan, where gauges picked up rises of a few inches. A wave of 4.5 feet is not the towering wall that the word tsunami brings to mind. It is still dangerous. Moving water at that height carries enormous force, can sweep a person off their feet, and can flood low shoreline streets and fish ponds. But it was far from the catastrophe that a larger or shallower quake might have sent. By the afternoon, the danger had passed, and the Institute lifted the warning. The sea had done its worst within a few hours, as local tsunamis do, and the threat of further waves faded with the largest early aftershocks. Lifting a warning is its own careful judgment. Officials had to be confident the sea had settled before telling people it was safe to return to the coast. They waited until the gauges and the aftershock pattern gave them that confidence, then stood the alert down. The whole tsunami episode, from first warning to all clear, ran its course in a single day. That this part ended as lightly as it did was partly luck and partly the depth of the break. A shallower thrust, or one that lifted the seafloor more sharply, could have sent a far higher wave into the same crowded coast. The region knows this in its bones. The Great Moro Gulf earthquake of the 1970s, in these same southern waters, sent a wave that killed thousands, and most of those deaths came from the sea, not the shaking. Set against that memory, a 4.5-foot wave that was warned for in minutes and gone by afternoon counts, as a hard day survived rather than a disaster endured. The episode also left people with a lesson they can carry, and the Institute repeated it plainly. Near the coast, the earthquake itself is the warning. There are 3 natural signs to know. A strong quake that is hard to stand through is the shake. A sudden, strange rise or fall of the sea along the shore is the drop. A loud roar from the water is the roar. Any one of them, near the coast, means move to high ground at once, and do not wait for an official message. For a local tsunami, the few minutes you save by trusting those signs can be the whole difference. The sea settled by evening. The ground did not. While the tsunami warning was being lifted, the aftershocks were still coming. The coast was standing higher than it had that morning, and the long work of counting the damage and the lost was only beginning. The second half of this report turns from the machinery beneath the sea to what all of it meant on land, starting with that risen coast and the families whose lives ran along it. After the quake, parts of the Sarangani coast stood higher than they had the day before. The same thrust that pushed the seafloor up offshore also lifted the land along stretches of the shoreline. The change was not dramatic to look at, a matter of a few feet in places, but along a coast it shows itself clearly. The tide no longer reached where it used to. Rocks and reef flats that had always been underwater now sat exposed at low water. Boats that had floated at their moorings found themselves resting on mud. The line between sea and land, fixed in living memory, had quietly moved. For the fishing families of towns like Glan and Kiamba, this was not a curiosity. It was their working world rearranged overnight. A boat ramp built to meet the water now ended above it. Fish traps and shallow farming pens sat in the wrong depth. Men who had launched from the same beach their whole lives had to relearn it. The uplift took a livelihood that depended on knowing exactly where the water sat, and made that knowledge wrong in a single morning. Some resort owners along the same shore worried over the opposite problem, a beach suddenly wider and a waterline pushed out from where their guests expected it. The uplift also told the scientists something useful, which is worth pausing on. The amount the land rises during a quake is a direct record of how the fault moved below. By measuring how much the coast lifted and where the lift was greatest, researchers can work backward to map the slip on the fault, how far the two sides moved and along which patch. The risen shoreline became a kind of ruler laid across the event, a permanent mark of a break that no one saw, written into the coast where anyone could read it. The sea gauges measured the wave. The land itself measured the slip. Coastal uplift of this kind is one of the slow ways that islands are built. The southern edge of Mindanao did not rise by accident or for the first time. It has been lifted, quake by quake, over a very long time, as the subduction below jacks the land upward in small violent steps. The same machine that shakes the region also raises it. A geologist walking that coast can read older lifted terraces, the marks of past earthquakes, stacked like steps above the current shore. This event simply added the newest step, and the families living on it felt the cost of standing on ground that is, over the ages, still being assembled. There was a human edge to the change that went beyond fishing. Risen ground can wreck the plumbing of a coast. Wells that drew fresh water near the shore can turn salty or run dry as the water table shifts with the land. Drainage that relied on the old slope of the ground can back up. In towns already short of clean water before the quake, the uplift made a hard problem harder. The mayor of one Sarangani town said plainly that water, not rubble, was his community's worst trouble in the days after, and the changed ground was part of why. It is easy to treat the uplift as a strange side note, but it belongs at the centre of what this earthquake was. A great subduction quake does not only shake, it moves the surface of the planet permanently, lifting some places and dropping others. The shaking ends in a minute. The new shape of the coast stays. Years from now, when the aftershocks are long forgotten and the cracked walls are rebuilt, the tide along parts of Sarangani will still meet the land at its new line, a quiet and lasting signature of the morning the fault slipped. The risen coast was the gentlest of the ground's lasting changes. Up in the hills behind the shore, the same shaking did something far more dangerous and far less tidy. Slopes that had stood for generations came loose, and the loosening did not stop when the main shock did. Each aftershock worked on ground that was already broken, and in the high country above General Santos that meant farms, homes and whole hillsides on the move. That is where the story turns next, from the coast that rose to the hills that fell. In the hills above the coast, the shaking pulled the slopes down. Steep ground and hard shaking are a dangerous pair. When a strong quake hits hill country, the jolt can break the grip that holds soil and rock to a slope, and gravity does the rest. Across the high ground of Sarangani, South Cotabato, and Davao Occidental, the Sarangani quake set off landslides, some small, some large enough to bury fields and block roads. From space, satellites later mapped the scars. Patches of green hillside turned to bare brown earth where the ground had slid. The total area stripped this way came to well over a square mile scattered across the southern uplands. One place stood for many. In a hinterland village above General Santos called Tal Salvan, landslides triggered by the quake-buried farmland that families had worked for years. A farmer there described harvests wiped out, fields swallowed under earth and rock. More than 400 residents could not go home. not because their houses had all fallen, but because the land around them had become unsafe and the slopes above them could still give way. Weeks after the main shock, they were still in makeshift shelters, kept from their homes by the twin fear of more sliding and more shaking. The reason the danger lingered comes straight back to the aftershocks. A single quake loosens a slope and brings down what is ready to fall. But it also leaves the hillside cracked and weakened, with tension cracks opening along the ground above the slip. Those cracks let water in and mark where the next failure will come. Then every aftershock gives the weakened slope another push. So the landslide risk did not end with the main shock. It rode along with the whole sequence, renewed each time the ground shook again, which is why officials kept telling people to stay off and away from cracked slopes for weeks. Rain made it worse, as it always does. Water is the other great trigger of landslides, seeping into cracked ground, adding weight and greasing the surface that the soil rests on. A slope left full of fresh cracks by an earthquake is primed to fail the next time heavy rain comes through. In a country that sees as much rain as the southern Philippines, that is not a distant worry. The Institute warned specifically that earthquake cracks could turn into landslides during heavy rainfall or further aftershocks, and asked people to report new cracks to local officials rather than wait and see. The standard guidance here is simple and worth stating plainly, because it saves lives. After a strong quake in hill country, treat steep slopes as dangerous. Watch for fresh cracks in the ground, for tilting trees or fences, for small trickles of soil and stone, and for the muddying of streams, all of which can warn that a slope is moving. If your home sits below a slope showing those signs, do not wait for it to fail. Move to safer, flatter ground, and report what you see so others can be warned. The advice is humble, but in landslide country, it is the difference between a near miss and a burial. Landslides are also why the toll from a great quake reaches places far from the epicenter and lingers long after the shaking stops. The shaking off Sarangani lasted a minute. The buried farms above General Santos will take far longer to recover, if they can be recovered at all, and the families displaced by unstable ground faced a wait measured in weeks and months, not days. A landslide does not just damage, it takes the land itself out of use, sometimes for good, and it does so quietly, up in the hills, away from the cameras pointed at the fallen buildings in town. There is one more way the ground itself turned against people in this quake, and it worked on flat land rather than slopes. In low places where the soil was loose and wet, the shaking did something that surprises people the first time they learn of it. It turned solid seeming ground for a few terrible seconds into something that behaved like a liquid. That process has a name and a clear cause, and it explains why two houses on the same street can meet such different fates. In some low, wet ground, the shaking turned soil into something like a liquid. The process is called liquefaction, and it sounds stranger than it is. In loose, waterlogged soil, the grains are not packed tight. They sit loosely, with water filling the spaces between them. When a strong quake shakes that ground hard enough, the grains are jostled apart and for a few seconds the water carries the load instead of the grains. The soil loses its strength and behaves like a heavy fluid. Anything resting on it, a house, a road, a wall, can sink, tilt, or slide, as if the solid ground had briefly turned to thick mud. This is why the damage from a great quake can look so uneven and almost unfair. Two houses, built the same way, standing on the same street, can meet opposite fates. The one on firm ground rides out the shaking with cracks. The one 100 feet away, over an old stream bed or filled-in marsh where the soil is loose and wet, tilts or partly sinks as the ground beneath it liquefies. The difference is not the building. It is the few feet of earth underneath, invisible from the surface until the shaking reveals it. People who lived through the quake often could not understand why their home stood while a neighbour's failed. The answer was buried below them. Liquefaction favours particular places, and knowing them is useful. Loose sandy soils, recent river deposits, reclaimed land, and the soft ground near coasts and old waterways are the most prone. Higher, older, rockier ground is far safer. Along the coastal plains and river valleys of southern Mindanao, where towns naturally grew up on flat, easy ground near water, there were patches of exactly the soil that liquefies. Where the shaking found them, it left the telltale marks, ground that had slumped, sand that had been forced up to the surface, and structures sitting at angles they were never built to hold. The same soft ground does something else that compounds the danger. It amplifies the shaking. Hard rock passes a quake's waves through quickly and cleanly. Soft, loose soil catches those waves and shakes them harder and longer, like jelly wobbling on a plate long after the plate itself goes still. So a town on soft ground feels a stronger, longer quake than a town the same distance away on rock, even before any liquefaction begins. The soil that is most likely to turn to liquid is often the same soil that shakes the worst, a double penalty for building on low, easy ground. None of this is new to the people who study Philippine hazards, and that knowledge has a practical use. Hazard maps mark the areas where liquefaction and strong amplification are most likely, and those maps are meant to guide where and how people build. A house on known soft ground can be built on deeper, firmer foundations to resist it. The trouble, as everywhere, is that the flat, soft, low ground is also the cheapest and easiest to build on and the most crowded. Knowing the risk and being able to avoid it are not the same thing for a family with few choices. Liquefaction, landslides, and uplift together make a single point. A great earthquake is not only a matter of how hard the ground shakes, it is also a matter of what the ground is made of and how it sits. The same magnitude can spare one place and ruin another, depending on the soil, the slope, and the water below. That is why the felt intensity of a quake, the actual violence experienced at a given spot, matters as much as the magnitude measured at the source. And to see how this quake was felt where the most people stood, we turn to the city nearest the break. 15 miles from the break stood a city of more than 500,000 people. General Santos is the largest city near the epicenter, a busy port and tuna fishing hub on the southern coast of Mindanao. When the fault slipped offshore, the city took some of the hardest shaking of any populated place. On the official Philippine intensity scale, General Santos recorded the level called destructive, which is high on a scale that tops out only a couple of steps above. For a city that size, sitting that close to a great quake, destructive shaking is a serious blow, and it showed in cracked buildings, fallen goods, and frightened crowds pouring into the streets. It is worth separating two ideas that people often mix up, because the difference is the whole point of this chapter. Magnitude measures the size of the earthquake at its source, the total energy the fault released. There is only one magnitude for a quake. Intensity measures how strongly the ground actually shook at a particular place, and it changes from town to town. A single quake has one magnitude but many intensities, high near the break and fading with distance. The 7.8 was the magnitude. The destructive shaking in General Santos was the intensity there. Farther away, the same quake was felt as merely strong, then moderate, then a faint sway. The intensity scale used in the Philippines runs in plain descriptive steps, and that is its strength. It does not lead with numbers. It describes what people feel and what happens to things. At the lower levels, hanging objects swing and light sleepers wake. In the middle, walls crack, furniture moves, and people find it hard to stand. At the destructive level General Santos saw, many buildings suffer real damage, weak structures fail, and the ground itself may crack or slump. The scale is built so that anyone, without an instrument, can place their own experience on it just by describing their morning. Reading the spread of intensities across the south tells the story of the quake's reach. The very strongest shaking, the most violent level, was estimated for a small area in western Sarangani, close above the break, where only a few thousand people live. A step down, the severe level, covered a far larger zone holding more than 1.5 million people, including General Santos, Glan and Palomaloc. Step down again to strong shaking, and the population exposed runs into the millions, reaching cities like Cotabato and Tagum well inland. The same quake touched a small number of people with its worst and millions more with its lesser blows. This is why the human cost of a great quake depends so much on who happens to live near the break. A magnitude 7.8 under an empty stretch of ocean or desert might harm almost no one. The same quake under a dense city would be a catastrophe of a different order. The Sarangani break sat offshore, with its most violent shaking falling on a thinly settled patch of coast, and its severe shaking reaching the cities just inland. That geography, more than anything, set the scale of the loss. The earth chose where to break. The map of towns decided what that break would cost. For the people of General Santos, the abstractions fell away the moment the shaking started. A police official described it as the strongest quake the city's residents had ever felt. In a commercial building, furniture toppled and appliances slid. Cracks ran up the walls of structures that had stood through smaller quakes without a mark. Workers and shoppers crowded outside, unwilling to go back in, and they were right to wait, because the aftershocks that followed would test those cracked walls again and again through the day. Behind every intensity number and every cracked wall were people, and some of them did not come through. The shaking that the scales measure so carefully fell on homes, schools, and streets full of lives. To honour what this quake actually meant, the report has to set the science aside for a chapter and count. Plainly and without inflation, the human toll of the morning the ground broke. By the third week after the quake, the confirmed toll had settled into hard numbers. At least 77 people had died. More than 1,300 were injured. 31 remained missing, a count that families and rescue teams still hoped to lower, but feared they could not. These are the figures the National Disaster Agency had verified by the third week of June, and they will likely shift a little as outlying areas are reached and reports are confirmed. The honest way to give them is as the best current count, exact where it can be and open where it cannot. The dead were not spread evenly. The toll fell hardest where the shaking was worst and the buildings weakest. Sarangani province lost the most, with 33 confirmed dead. South Cotabato lost 24, most of them in General Santos. Davao Occidental lost 20, with single deaths in a few other provinces nearby. Behind that simple breakdown is the geography of the quake made personal. The provinces closest to the break, the ones that felt the severe and destructive shaking, are the ones that buried the most people. Distance from the fault, in the end, was measured in lives. Most of the deaths came the way they usually do in earthquakes, from falling debris and collapsing structures. People were struck by failing walls, by toppling concrete, by roofs and ceilings coming down. This is the grim, consistent truth of earthquake death worldwide. The shaking itself does not kill. Buildings kill. A quake of this size in open country would harm almost no one. The same quake among heavy, poorly braced structures takes a heavy toll. Every life lost off Sarangani was, in a sense, lost to a building that could not hold, which is why so much of earthquake safety is really about how and where we build. The injured outnumbered the dead many times over, as they nearly always do, and their suffering did not end when the shaking stopped. More than 1,300 people hurt is a vast strain on hospitals that were themselves shaken, some damaged, all suddenly overwhelmed. The health authorities put their crisis protocols into effect across Mindanao, doing rapid checks of which hospitals could still function, and moving the hurt to where they could be treated. Injuries from a quake range from cuts and broken bones to the crushing wounds that need urgent advance care, and they all arrive at once, in the same hour, on a medical system that has just been hit. The damage to buildings underlay all of it. More than 84,000 homes across Mindanao were damaged or destroyed, along with schools, offices and public facilities. In the school system alone, hundreds of classrooms were severely damaged or destroyed, and more than 1,000 took lighter damage. That this quake struck on a Monday morning, with schools in session, makes the classroom damage especially sobering, though by fortune the worst building failures spared the children inside the ones that were reported. The cost to repair and rebuild runs into the tens of millions of dollars for schools alone, and far more across all the homes and infrastructure lost. These numbers deserve to be read slowly, not rushed past. 77 people who woke that Monday did not see Tuesday. 31 families were left waiting for word that may never fully come. More than 1,000 carried injuries, and tens of thousands lost the homes they returned to each night. The science in this report explains the why and the how, and it matters, but it sits underneath a simple human fact. A region went about an ordinary morning, the ground broke, and lives ended. No explanation softens that, and none should try to. For those who lived, the days after the quake were not a return to normal, but a long stretch of fear, with the aftershocks keeping the danger and the dread alive. How people endured that, and the plain steps that kept them safer through it, is the next part of the story. For weeks after the quake, many people would not sleep inside. The reason was the aftershocks. with the ground shaking again and again, often dozens of times a day in the early stretch. Going indoors felt like a gamble. A house that had cracked in the main shock might hold through 10 aftershocks and fail on the 11th. So people did the rational thing. They stayed out. Families slept in yards, on roadsides, in tents and lean-tos, anywhere a falling roof could not reach them. By day, some ventured inside to cook or fetch belongings, then came out again at night. The fear was not irrational. It tracked a real and continuing danger. This is one of the least visible costs of a long aftershock sequence, and one of the heaviest. The exhaustion of it wears people down. Sleeping outside in the heat and rain, jolted awake by each new tremor, never sure if the next one will be small or strong, takes a toll on the body and the mind that does not show up in the damage reports. In one of the affected towns, a Red Cross worker described how people would act as if life were normal, and then another aftershock would come, and the fear would return all over again. That cycle, repeated for weeks, is its own kind of injury. The displaced needed the basics, and providing them was the first work of the response. Thousands of families crowded into evacuation centres or camped near their ruined homes, and they needed water, food, and shelter at once. In some towns, the hardest thing to supply was clean water, a problem the quake had worsened by damaging wells and shifting the ground. Aid groups and the government moved to bring in water tankers, filtration units, food, and tents, while the Institute kept issuing its aftershock updates so people could judge the danger for themselves rather than guess. Through all of it, the official safety guidance stayed simple and steady, and it is worth setting down plainly because it works. When strong shaking starts, drop to the ground, take cover under sturdy furniture and hold on until it stops. Do not run outside during the shaking when falling debris is most likely to strike you. Once the shaking ends, then move calmly to open ground away from walls and power lines. Keep heavy furniture and appliances anchored to walls so they cannot topple in the next shock. And stay out of buildings that are visibly cracked or weakened, because those are the ones an aftershock is most likely to bring down. That last point carried the most weight in the weeks after this quake. The greatest danger during a long aftershock sequence is the damaged building re-entered too soon. People understandably want to go home, to retrieve belongings, to sleep in their own beds. But a structure wounded by the main shock is exactly what the next strong aftershock can finish. The Institute urged people not to go back into damaged buildings without a proper safety check by qualified engineers. It is hard advice to follow when home is right there, cracked but standing. It is also the advice most likely to keep a survivor alive through the weeks that follow. There is a calmer truth folded into the fear, and people deserve to hear it too. The aftershocks, frightening as they were fading along that long Amori curve from earlier in the report. Each week brought fewer and smaller shocks than the week before. The danger was real but shrinking, and the science could say so honestly. Knowing that a sequence winds down, even without a clean end, gives people something to hold on to. The fear says it will never stop. The pattern says, quietly and reliably, that it is already easing. Both things were true at once, and the second one mattered. Holding people steady through that stretch fell to the agencies that watch the ground and call the warnings. Their work happened mostly out of sight, in monitoring centres and on instrument networks, but it shaped every decision people made, from when to evacuate the coast to when it was safe to return. That quiet machinery of warning is worth understanding, because it is the reason a great quake in 2026 killed dozens rather than thousands. The warnings that guided the region came from a single national agency and its network of instruments. The Philippine Institute of Volcanology and Seismology is the body that watches the country's earthquakes and volcanoes, and it ran the official response to this quake from the first minute. It determined the magnitude, located the break, issued the tsunami warning, tracked the aftershocks, and put out the plain language advisories that told people what to do. In a disaster full of rumour and fear, it served as the single trusted voice, and it asked the public repeatedly to rely on its bulletins rather than on unverified messages, because false alarms in a frightened region can cause their own harm. Behind the agency stands a network of instruments spread across the whole country, 128 seismic stations in all. Several site close to the southern Mindanao coast, in General Santos, Kidapawan, Cotabato City, and Davao. When the fault slipped, The waves it sent out reached the nearest stations within seconds, and the farther ones soon after. By measuring the tiny differences in when each station felt the shaking, the agency could pinpoint where and how deep the break was, almost at once. The same instruments, running day and night, are what counted the thousands of aftershocks that followed. The tsunami warning shows how fast this machinery has to work. A local tsunami from a nearshore break gives people only minutes. There is no time to measure the wave first, so the warning is made from the earthquake alone. The moment the instruments showed a great quake at a shallow depth under the sea, the rule said a dangerous wave was possible, and the agency issued the warning on that basis, within minutes, before any water had moved. That speed is not luck. It is the product of instruments, procedures, and trained people all prepared in advance for exactly this morning. The minutes it bought are the minutes people used to climb to higher ground. Calling the all clear takes a different kind of judgment, slower and just as careful. Once the waves had come and the gauges showed the sea settling, the agency had to decide when the threat had truly passed before telling people it was safe to return to the coast. Lift the warning too early and you send people back into danger. Lift it too late and you keep them from their homes and erode their trust for next time. The agency waited until the measurements and the aftershock pattern gave it confidence, then stood the warning down that same afternoon. Both the raising and the lifting were deliberate acts, each weighed against real costs. The agency also leaned on history, because the past is one of the best guides to the present in earthquake country. It could tell the public that this region had produced major quakes before, that the Cotabato Trench was a known earthquake-generating structure, and that at least 7 significant quakes had struck Sarangani and its neighbours over the past century. That context matters. It let officials say, honestly, that this event was severe but not unprecedented, that the region had survived such mornings before, and that the aftershocks would behave as aftershocks always do. Calm grounded in record is steadier than calm asserted from nowhere. None of this machinery prevents earthquakes. Nothing can. What it does is turn a sudden catastrophe into something a little more survivable, by giving people warning where warning is possible, by counting the aftershocks so the danger can be judged, and by speaking clearly so fear does not fill the silence. A great quake under a populated coast that kills dozens is a tragedy. The same quake without warning, without monitoring, without a trusted voice, would likely kill far more. The difference between those two outcomes is the quiet work of agencies like this one, done well in the hours when it counts. To understand how unsurprised the scientists were by this event, it helps to look back at what this same region has done before. The southern Philippines has a long and heavy earthquake record, and one event in particular hangs over every quake that strikes these southern waters. This region has produced a far deadlier earthquake within living memory. In the year 1976, a magnitude 8 earthquake struck the Moro Gulf in these same southern waters off Mindanao. It was larger than the 2026 quake, and it was followed by a tsunami that swept the coasts of the Gulf at night, when people were asleep and could not see it coming. The toll was catastrophic. Thousands of people died, most of them to the wave rather than the shaking. It remains one of the deadliest natural disasters in the country's history, and it is the event every Philippine seismologist measures southern Mindanao against. The 1976 disaster is why the tsunami response in 2026 was so fast and so serious. The institutions learned hard lessons from that night. They learned that a nearshore quake in these waters can send a deadly wave within minutes, that a warning has to go out on the earthquake alone, and that the public has to be taught the natural signs so they can move without waiting for a message. The 4.5-foot wave off Sarangani, warned for in minutes and survived, was in part the dividend of a lesson paid for in thousands of lives half a century earlier. The region remembered, and the remembering saved people. The comparison also sets the recent quake in honest proportion. A magnitude 8, like the 1970s event, releases roughly twice the energy of a magnitude 7.8. The crust here can clearly produce earthquakes larger than the one that struck in June. That is not a reason for alarm, but it is a reason for respect. It means the 7.8, severe as it was, sat within the range this region has shown before, not beyond it. The ground did nothing in 2026 that it had not done, more terribly, within the memory of people still living. The southern Philippines has kept shaking in the decades between, in smaller but still damaging steps. The Institute noted that at least 7 significant earthquakes, ranging widely in size, had struck Sarangani and its neighbouring provinces across the past century. The most recent damaging one before this came in late 2023, a magnitude 6 8/10 quake in the same general area. So the region has a steady record of moderate to large earthquakes, spaced years apart, each one a reminder that the subduction below never rests. The 2026 quake was the largest in a long line, not a bolt from a clear sky. This long record is what let the scientists stay calm while the ground would not. They were not watching something new and frightening. They were watching a known, well-studied, dangerous region do the thing it has always done, on a schedule no one can predict but a pattern everyone in the field understands. The Cotabato Trench loads, locks, and breaks. It has done so for as long as there have been records, and the records reach back far enough to make the behaviour familiar. Familiarity does not make the loss any lighter. It does make the science confident. There is a comfort and a warning braided together in this history, and both are true. The comfort is that the region has survived earthquakes like this before, that the response improves with each one, and that the science understands what is happening well enough to guide people through it. The warning is that the subduction below will not stop, that larger quakes than this one are within its power, and that the only real defence is the slow, unglamorous work of building stronger, mapping the hazards, and remembering the lessons each disaster teaches. The ground will shake again. The only question is how ready people are when it does. That long record raises a question many people in the South were asking in the days after, often quietly, sometimes aloud, and it is a question worth answering honestly. Within the same recent stretch, another part of the country had been badly shaken too. People wanted to know whether all this shaking was connected, whether the country's faults were somehow waking together. The answer requires care, and it begins with a quake that struck far to the north only months before. Months earlier, a different part of the country had been badly shaken. In late September of 2025, a magnitude 6 9/10 earthquake struck off northern Cebu, in the central Philippines, hundreds of miles north of Sarangani. It was the strongest quake recorded in that area, and it was deadly, killing dozens and damaging tens of thousands of homes. It too produced a long and heavy aftershock sequence, more than 12,000 shocks over the following weeks. For many in the country, the Cebu quake and the Sarangani quake, coming within a single year, raised an uneasy question. Was the whole archipelago somehow shaking loose at once? The honest answer is no, not in the way the question imagines. The Cebu quake and the Sarangani quake happened on different faults, in different regions, driven by different parts of the country's tectonic machinery. Cebu's quake came from a previously little-known fault that had been quiet for centuries. Sarangani's came from the subduction at the Cotabato Trench far to the south. They are too far apart and too separate in their mechanics for one to have triggered the other. Each was its own event, loaded over its own long span of years, breaking on its own schedule. Their nearness in time was coincidence, not connection. It is worth being precise about why distant quakes almost never trigger each other, because the intuition that they must is strong and wrong. The stress changes that one earthquake sends through the crust are large close to the break and fade very quickly with distance. A few tens of miles away, a quake can meaningfully load a neighbouring fault. A few hundred miles away, the effect is vanishingly small, far too weak to break a fault that was not already on the very edge of failing on its own. Cebu and Sarangani are separated by exactly the kind of distance that rules out a direct push. The faults did not feel each other in any way that matters. What the two quakes do share is a common parent, and that is the real link worth naming. The Philippines sits on the Pacific Ring of Fire, in a crowded collision of several plates, threaded with trenches and faults along its whole length. The whole country is earthquake country, top to bottom, and always has been. So a year with two major quakes in different regions is not a sign of something new awakening. It is a sign of what the Philippines simply is, a place where many faults are loading at once, each on its own clock, and where two of them happening to break in the same year is unusual but not extraordinary. The shared cause is the country's tectonic setting, not a chain reaction between faults. This distinction matters for how people understand their own risk. If quakes triggered each other across the whole country, then every distant earthquake would be a reason to fear yours was next, and there would be no rest. Because they do not. The risk in any one place depends on its own local faults and their own local loading, which can be studied, mapped, and prepared for. The Cebu quake told the people of Sarangani nothing about when their ground would break, and the Sarangani quake tells the people of Cebu nothing about theirs. Each region must watch its own faults. That is harder in one sense and far less frightening in another. There was a real and tragic connection between the two events, but it was human, not tectonic. Both quakes struck a country already stretched by repeated disasters, by typhoons and floods and earlier earthquakes falling on the same communities again and again. The damaged compounds, families still rebuilding from one disaster are hit by the next. Aid and money and attention are stretched thin across too many emergencies. That is the true way the country's disasters connect, not through the rock, but through the people who must absorb them and the strain of facing one after another with too little time to recover between. With the separate faults understood, the question that weighed most heavily on the people of Sarangani was not about Cebu at all. It was about their own ground and whether the worst was truly over. That is the hardest question in this whole report, the one where the science stays honestly uncertain, and it deserves a careful and unflinching answer. The question everyone wanted answered was whether a bigger quake was still coming. It is the natural fear after a great earthquake, sharpened by every aftershock. People want a promise that the worst is behind them. Honest scientists cannot give that promise, and the Institute did not. What they can give is the shape of the odds, drawn from how earthquake sequences behave, and the shape is reassuring without being a guarantee. After a great quake, the most likely future by far is a long, fading run of aftershocks, each smaller on average than the last, with the largest already past. But likely is not certain, and the gap between them is where honesty lives. Start with what the rules say. Both's pattern, from earlier, holds that the largest aftershock tends to fall about a step below the main shock, which off Sarangani it did, at magnitude 6 7/10. Omori's pattern holds that the shocks fade steadily over time. Together they say the same thing. Once a magnitude 7.8 is struck, the odds strongly favour that it was the main event, that the aftershocks will stay below it, and that they will grow fewer and weaker as the weeks pass. That is the expected path, and the Sarangani sequence was walking it. Now the uncertainty, stated plainly. There is always a small chance, after any large quake, that an even larger one follows. When that happens, the first quake is renamed a foreshock, and the new giant becomes the main shock. This is rare. The great majority of large earthquakes are not foreshocks to something bigger, but it does happen, and no one can rule it out in the first days and weeks. So the Institute told people to prepare for aftershocks and to keep clear of weakened buildings, precisely because it could not promise that the largest shock had already come. That was not alarmism. It was refusing to claim a certainty that does not exist. The region's own history sharpens the point. This same stretch of southern waters produced a magnitude 8 in the 1970s, larger than the recent quake. So the crust here is capable of bigger events than the 7.8. That does not mean another is coming soon. The 1970s quake and the 2026 quake may be separated by centuries on their particular faults. But it does mean that the possibility of a larger quake in this region someday is real, and that the recent event did not somehow use up the danger. Subduction zones do not empty out, they reload. What scientists will not do is predict the day. There is no method anywhere in the world that can say a specific large earthquake will strike on a specific date. Anyone claiming otherwise is wrong or worse. What the science offers instead is probability and preparation. It can say this fault is dangerous, this region is loaded, this kind of shaking is to be expected here. Build accordingly and be ready. It cannot say it will happen next Tuesday. That limit is not a failure of effort. It is a real feature of how earthquakes work, and accepting it honestly is wiser than chasing a prediction that cannot be made. So the honest answer to the question is layered, and people deserve all the layers. The worst is very probably over, because the rules say so, and the sequence is behaving. A larger quake is unlikely but not impossible, because rare things happen and the region can produce them. No one can name the day of any future quake, here or anywhere. And the right response to all of that is not fear but readiness. The steady, unglamorous work of strong building and clear planning that pays off whenever the ground next moves. That is the most the science can truthfully say, and saying exactly that much, no more and no less, is what keeps trust intact. With the big question answered as well as it can be, the practical matter remains. People living over this fading sequence still need to know what to watch for in the days and weeks ahead, and there are a few real signals worth keeping in view. In the weeks ahead, the sequence will keep fading, but a few things are worth watching. The first is the aftershocks themselves, growing fewer and smaller along that long curve. This is the expected and welcome pattern, and tracking it is genuinely useful. When the Institute reports that the daily count has dropped, that the largest recent shocks are smaller than the early ones, that is the sequence doing what it should. People can take real reassurance from those numbers, because they are the measurable sign that the danger is easing. The fading is not a feeling or a hope. It is a trend the instruments record, week by week, and it has been pointing the right way since the first day. The second thing to watch is the offshore shocks in particular, because of the sea. Most aftershocks are too small to matter beyond a rattle, but the sequence sits partly under the water, and a large enough aftershock offshore could, in principle, stir another small tsunami. This is unlikely, since the aftershocks are fading, and a wave needs a sizable shallow break to form. But it is the reason coastal communities should stay alert to the natural warning signs even now, weeks on. A strong quake felt at the coast, a sudden change in the sea, a roar from the water, any of these still means move to high ground at once, no matter how far the sequence has faded. The third is the slow danger up in the hills. The landslides triggered by the quake left, slopes cracked and weakened across the southern uplands, and those slopes will stay dangerous for some time, especially when the rains come. A hillside that held through the dry weeks after the quake can still fail in a heavy downpour, the water seeping into earthquake cracks and pulling the loosened ground down. People living below steep cracked slopes should keep watching them, report new cracks, and be ready to move if the warning signs appear. The shaking has mostly passed. The landslide risk it created has not. The fourth thing to watch is the buildings, and this is where care is most needed and most often dropped. As the fear fades and life pushes people to return to normal, the temptation grows to move back into damaged homes and reopen cracked buildings. That temptation is the quiet danger of the recovery phase. A structure wounded by the main shock and battered by aftershocks needs a proper inspection before anyone trusts it again. The right step is to have damaged buildings checked by qualified engineers and to wait for that check rather than guess. It is slow and inconvenient, and it is exactly the discipline that prevents the late, avoidable deaths that sometimes follow a quake long after the shaking stops. Beyond those immediate watch points sits the longer work, the part that matters most over years rather than weeks. This quake will be studied closely. Scientists will map the slip on the fault from the risen coast and the recorded waves, refine which trench broke and by how much, and fold the lessons into the hazard maps that guide future building. The recovery too is a chance to rebuild stronger, to repair schools and homes to better standards, to take the hard knowledge this disaster brought and turn it into safety for the next one. That work is slow and easy to neglect once the cameras leave, and it is the most valuable thing the region can do with what it has suffered. For the people of Sarangani and its neighbours, though, the next weeks are simpler and more human than any of that. They're about getting clean water, getting children back to school, getting roofs repaired and livelihoods restarted, all while the ground gives its last fading shudders beneath them. The science can explain what happened and what to watch for. The recovery is daily, ordinary, and theirs to live. And as it goes on, the strangeness that gave this report its title settles into something steadier, and, in its own way, more reassuring than fear. The aftershocks that seemed impossible were the most ordinary thing about this earthquake. That is where the whole story comes to rest. To the families standing in the street feeling the ground lurch for the 10th and 20th and 50th time, it felt as if the earth had thrown out its rulebook. It had not. Every shock had a cause. The main shock left stress piled in the crust. The stress let go in pieces, and each piece was an aftershock. The count was huge because the break was huge, and the ground was crowded with faults. The fading followed Amori's century-old curve. The largest aftershock sat a step below the main shock, just as Both's rule says it should. From the first jolt to the last fading tremor, The sequence behaved exactly as the science predicts. Nothing about it broke a single law. What was extraordinary was never the behaviour, it was the place. The break happened at a tangled junction where the Cotabato Trench meets the northern arm of the Sangihe Trench, on the doorstep of the one spot on Earth where a plate is being swallowed from both sides at once. That crowded, double-loaded crust was always going to turn a great quake into a long, wide, hard-running swarm. The strangeness people felt was real, but it lived in the geology of the ground, not in any failure of the ground to obey its rules. The Earth followed its laws perfectly. It just did so in one of the most unusual corners of the planet. So what is known, plainly? A magnitude 7.8 earthquake struck off Sarangani on a Monday morning, the strongest in the country in nearly 50 years. It killed at least 77 people, injured more than 1,000, and left 31 missing. It sent a small tsunami that was warned for in minutes and survived. It lifted the coast, loosened the hills, and shook a busy city to its foundations, and it set off thousands of aftershocks that frightened a region, but followed every rule in the book. What is still uncertain, stated just as plainly. The exact split of the rupture between the two trenches is still being worked out. The final toll may shift as outlying areas report, and no one can promise that the largest shock has come, only that the odds strongly favour it. These are not gaps in the story. They are the honest edges of it, the places where good science says how much it knows and no more. What to watch is simple. The aftershocks fading week by week, which they are. The offshore shocks that could still stir the sea, which grow less likely by the day. The cracked slopes that the rains could pull down, and the damaged buildings that need a proper check before anyone trusts them again. None of these is cause for fear. All of them are cause for steady, ordinary care, the kind that carries a region safely through the long tail of a great quake. In the end, the title asked a fair question, and the ground gave a quiet answer. The aftershocks did not break the laws of physics. They demonstrated them, in a place built to put on the demonstration. There is something steadying in that, once the fear settles. The Earth is not capricious, it is lawful, even at its most violent, even when it shakes a coast for weeks. Understanding the law does not stop the shaking, but it does something almost as valuable. It replaces dread with knowledge, and knowledge is what lets people rebuild, prepare, and stand on this ground again with clear eyes. That is the report from off Sarangani. The ground is still settling, the recovery is just beginning, and the science will keep watching the fading sequence in the weeks to come. We will follow it as it does. Until the next report, stay aware, stay prepared, and rest a little easier knowing the ground keeps its rules.